Scientists in China have developed a real-life invisibility cloak. This groundbreaking camouflage material has the remarkable ability to dynamically adjust its molecular composition to seamlessly blend with its surroundings, potentially rendering the wearer invisible to the naked eye. The secret behind this vanishing act lies in a process called self-adaptive photochromism, or SAP. This involves a unique molecular rearrangement within the material when exposed to specific wavelengths of light, causing it to change color and effectively disappear into the background. This mechanism is similar to the natural camouflage abilities observed in chameleons and octopuses, where they adapt their skin color to match their environment. Unlike these creatures, which rely on specialized pigment-containing cells, the SAP material is composed of organic dyes and molecules called donor-acceptor Stenhouse adducts. These components undergo chemical and structural transformations upon exposure to light, triggering the color change. The material, initially black in the dark, dynamically shifts its pigment in response to the transmitted and reflected light from its surroundings. To test its effectiveness, researchers conducted experiments where they placed the SAP solution in containers of various colors and observed its ability to adapt its hue accordingly. Further tests involved placing the material in an environment with different colored plant clusters, where it successfully blended in within a minute. The SAP material can be applied as a spray-on coating, making it more versatile and cost-effective.
Future smartphones may be able to recharge themselves without any external power source. Scientists have created wire-free transparent solar cells that can be integrated into the glass of smartphones, vehicles, and structures, providing an unobtrusive and effective method for harnessing solar energy. This innovative design features an all-back contact configuration, placing all electrical contacts on the rear side to create a glass-like transparent crystalline silicon cell. The solar module successfully charged a smartphone using natural sunlight, demonstrating its practical application in creating self-charging smartphones. This development fundamentally solved the aesthetic problem of the existing solar cell modularization method. Transparent silicon solar cells have potential applications across various industries, including small devices, buildings, and automobile glass. In consumer electronics, these cells could be integrated into smartphone screens, tablet displays, and laptop lids, allowing devices to charge themselves while in use or when exposed to sunlight. In the automotive sector, car windshields and sunroofs could be equipped with these cells, supplementing the vehicle's power system and potentially extending the range of electric cars. The construction industry stands to benefit greatly, as these cells could be incorporated into building windows, skylights, and glass facades, turning entire structures into power generators without compromising aesthetics or natural lighting. In agriculture, transparent solar cells could be used in greenhouse roofing, generating power while allowing necessary light to reach the plants.
A metal that can heal itself has been discovered by scientists. During an experiment, they observed that pieces of metal spontaneously crack and then fuse back together without any human intervention. This newfound phenomenon has the potential to revolutionize engineering, opening the door to applications such as self-healing engines, bridges, and airplanes. The scientists had been attempting to evaluate how cracks formed and spread across a piece of platinum. To observe this, the scientists used machinery that pulled the metal's ends 200 times per second. They were stunned to watch the cracks heal themselves in real time. Repeated motions can often cause something known as fatigue damage on machines. This damage leads to cracks, which expand over time and can eventually end a machine's working life. This self-healing property in metals could offer a solution to these issues. However, the newly discovered mechanism only works on a few metals and on incredibly small scales, at least for now. Further research is needed to fully understand and harness this phenomenon, including whether it can be induced in conventional metals outside of a vacuum environment. The implications of such a breakthrough could be far-reaching, benefiting industries and economies worldwide.